In this section, we're going to be using balanced chemical equations to relate amounts of different substances within the reaction. That action of relating the amounts of substances within the reaction is called stoichiometry. This example of a balanced chemical equation could be read: 2 moles of CO plus 1 mole of O2 makes 2 moles of CO2. However, we aren't just limited to using the exact numbers that are given in the equation. I could put 2 moles of CO into my beaker, or I could put 6.7 moles of CO into my beaker. I'm not required to put a certain amount into my beaker. We can still use the same equation, but the equation just tells us the ratios of the things that are reacting. It tells us that for every 2 moles of CO that react, 1 mole of oxygen will be reacting along with it to make 2 moles of CO. We can use the coefficients as ratios to calculate the amounts of anything in the reaction. If I know the amount of CO that I'm putting into it, I can figure out how much CO2 I ought to get out of it. If I know the amount of CO2 that I got out of it, then I should know how much CO went into it to begin with. We're going to be using a set of conversion factors, which we'll call stoichiometric factors. In stoichiometric factors, the coefficients from the balanced chemical equation will relate the number of moles of one thing in the reaction equation to moles of another thing in that same reaction equation. The moles of what we know are going to go on the bottom of our stoichiometric factor, since they'll end up canceling out, and the moles of what we're trying to solve for will go on the top. Then we'll just fill in the coefficients next to the correct units. Let's look at an example. We're trying to find how many moles of CO2 would be produced if 3.82 moles of CO is put into the reaction. We've got two options for conversion factors that relate moles of CO and moles of CO2 from this balanced equation. We could have a conversion factor with moles of CO2 on the top and moles of CO on the bottom, or we could have a conversion factor with moles of CO on the top and moles of CO2 on the bottom. The one we choose is going to depend on which unit we're starting with and which unit we're trying to solve for. First, we start with the number that we're given in the problem, 3.82 moles of CO. Then we'll choose a conversion factor that has moles of CO on the bottom in order to cancel out. And then moles of CO2 will be on the top since we're trying to solve for it. The twos that we fill in next to moles are the coefficients for our balanced chemical equation. There's a coefficient of 2 next to the CO and a coefficient of 2 next to the CO2. The equation has to be balanced before we can do any sort of stoichiometry. Our balanced equation tells us that for every 2 moles of CO that go into it, 2 moles of CO2 will come out. We fill our coefficients into our stoichiometric factor and then do our calculation. 3.82 divided by 2 times 2 gives us 3.82. The units on that end up being moles of CO2, which is a different unit than we started with, even though the number ended up being the same. Make sure you write out the full unit. Don't just write moles, and don't just write CO2. Write moles of CO2. Otherwise, you're going to get confused. We'll do some things later with grams or molecules, and there are multiple substances in each reaction, so it is really important to use the full unit, including type of substance. Here's another example with the same equation. We're still putting in 3.82 moles of CO. This time we're trying to find how many moles of oxygen are needed to react along with that amount of CO. Now we're not going from a reactant to a product or a product to a reactant. Instead, we're going reactant to reactant. We can go from anything in the equation to anything else in the equation as long as it's balanced. Again, we're going to start with our value that's known, our 3.82 moles of CO. We've got moles of CO on the bottom of our stoichiometric factor to cancel out. Moles of oxygen is what we're trying to solve for, so that goes on top. In our balanced chemical equation, there's a 2 next to the CO, so we write that next to moles of CO in our conversion factor. There's an understood 1 next to the oxygen in the balanced chemical equation, so we put that next to moles of oxygen in our conversion factor. We do 3.82 divided by 2, and we're dividing by 2 because that 2 is in the denominator. So we find out that 1.91 moles of oxygen are needed to react with 3.82 moles of CO. How many moles of oxygen are needed to react with 7.5 moles of aluminum? 4Al plus 3O2 makes 2Al2O3. Is it A, 5.6 moles of the oxygen molecule, B, 7.5 moles of the oxygen molecule, C, 10 moles of the oxygen molecule, or D, 22.5 moles of the oxygen molecule? The answer is A, 5.6 moles of oxygen. Since we want to find moles of oxygen goes on the top. We're going away from moles of aluminum, so moles of aluminum goes on the bottom. We have a 4 in the conversion factor next to the aluminum and a 3 in the conversion factor next to the oxygen. 7.5 times 3 divided by 4 equals 5.6.